object submerged. So we, we have some fluid, liquid in this case, and an object is submerged, and we know that pressure inside a liquid depends only on the depth. So we know pressure here is lower than pressure here. Therefore, there's a net force, obviously, pushing the object up. And the sum of those forces need to add up to the apparent weight. So if you remember doing a free body diagram of it, the actual weight of the object points down, the buoyant force points up, and therefore we can write down that the apparent weight of the object is the real weight minus the buoyant force. All right. Okay. So it turns out that the buoyant force.
Professor?
Yes.
Just a quick clarification. The actual weight is the mass times gravity, correct?
That's correct. That is correct. And I'll get there in a second. So yes, we already know from 2a that this is m times g. So we already know what an actual weight of an object in a gravitational field is. Okay? But when you submerge it in a liquid that is also in that same gravitational field, there is an extra force due to the pressure being larger at larger depths. There is a net force pushing the object up. Okay, and so and it turns out that the force of the buoyant force, the total force that pushes the object up, is equal to mass of the fluid displaced by object, okay, times g. Okay, so in other words, this is the weight. This is really the weight. This is the weight of fluid that was displaced by object. Now, what does that mean? Means, well, if the object is not there, that entire volume of the object would have been filled by the fluid itself. But now that object pushed that whole liquid away when it inserted itself in there. And so if you could find out the total weight of the liquid that was displaced or fluid that was displaced, that's the amount of the weight that the object loses. So we can write this down as weight apparent is equal to weight actual. Well, obviously this is mg minus weight of fluid displaced. Okay, now obviously this is mg, and the other one is mass of the fluid displaced times g, because that's the weight of the equivalent amount of that fluid that would have been there instead of that object. Okay, so that's, and I have to put vector signs here. Okay, so that's the apparent weight. And this is why objects, they feel less heavy when you submerge them in water. I mean, you guys have all played in a pool and you know things submerged way less due to this effect. Okay, so that's very simple. Let me keep on going with this thing. So this is mg, and this is mass of the fluid times g. Now, of course, mass of the fluid would be volume of the object times density of the fluid. Okay? So this is really how you calculate the apparent weight. You need that because the mass of the fluid that the object displaced would be the volume of the object times the density of the fluid. Right, so this is really the most useful form of this equation. And let's do an example so you know how to use it. Any questions so far? All right.
Just a quick question.
Yeah.
If the volume of like the volume of the object, if the object is an irregular, how I don't remember how to find the volume. Do you think you could go?
Right. Yes, there are ways of doing it. We'll talk about that in a second. So I'll answer that in a second. Usually in problems, you are given objects that their volume is easy to calculate. Okay? So the volumes are easily calculated because objects are easy. They're like a sphere, or they are cylinders or boxes, things like that. But one easy way of finding volume of objects is just you dip it in a cylindrical container that has some liquid in it, and then you know how much that liquid rises when you submerge the object. And from the volume of that displacement, you can find out the actual volume of the object. But we'll talk about that a little bit later. All right, so suppose I have a container. Okay, and it has some amount of fluid in it. Okay, and now I'm going to put a rectangular object that actually okay, so this object kind of halfway, it floats. The object is floating object. Okay? And it has a density of, this is density of the object. Let's say it's 1,000 kilogram per meter cubed. And then on the top, it has some surface area A, and it being rectangular in shape, that surface area doesn't change as you go down. And let's say the total height of it is capital H, and let's give it a 7 centimeter total height. And it is submerged, and the amount of submerged is a little h. And the question is, and of course this fluid, the fluid here has density of the, it's liquid. Let's say that's 1,400 kilogram per meter cube. Now the question is, what is height little h. In other words, how much of this box that is floating is under the surface of that liquid. All right. So that's the question. How do we solve this problem? Obviously, we need to start with, and this thing doesn't have any weight. Apparent weight of it is 0, obviously, because it's floating. It's not falling down and it's not flying off. So it is just floating. So the apparent weight is 0 because it's floating. Okay, so then 0 is equal to mg of the actual object minus the volume of the object displaced times rho of the fluid times g, which is the equation on the top. All right, so mass of the object is obviously the volume of the object times density of the object. And volume of the object, so I should there on top say submerged, and I should say submerged. Now the volume of this object that is submerged, only the portion that's submerged is equal to A times little h, and then rho of the fluid. Okay? All right, so let me write this down again. Rho object, V object 0, G minus okay. So now volume of the object. Now to go back to the drawing, the total volume of the object, because that's we need to find the total weight of it, and total mass of it is just capital H times area. Okay, so now I can factor out this object here and write capital H, rho of the object, minus little h, rho of the fluid, and that's equal to 0. That means this thing has to be equal to 0 because area is not and g is not. All right, so that means h, rho of the object, has to be equal to little h, rho of the fluid. And then we can calculate little h from this. Okay, so that's pretty neat. Now we can plug in those numbers. This was 7 centimeters. And then rho of the object was 1400. I'm sorry, the object was 1000 kilogram per meter cube, and this was 1400. Okay, so when you work this out, you get 5 centimeters. All right, so this is your h. So you can see this object, the amount of it, the length that it actually is below the fluid surface, the liquid surface is 5 centimeters, when the entire length of it is the height of it is actually 7 centimeters. So this is a pretty straightforward problem in calculating what they're asking, which is how much of it is underwater, using the the buoyant force. Now, this equation is really this whole concept that objects lose weight when they are submerged in a fluid is called Archimedes' principle. So I should write this down so you know what this is. This is really Archimedes' principle. Okay, this is Archimedes' principle just says whenever you submerge an object in water, it loses its weight by the amount of the weight of the displaced liquid or fluid. All right. Any questions? All right. So, when is your lab, guys, for 2A? Was it already done? It was yesterday? Okay, so you guys probably did this Archimedes principle experiment, correct? Yeah, so it is that. So the buoyant force is that. Okay, so that's what you guys did then. Now, I am trying to, I'm sure you guys have have seen things like this, and you've noticed that I do not plug in numbers until at the very end. Because if you plug in numbers, things become really hard to follow, and then you're prone to make mistakes. I like to keep things algebraically throughout the calculation, and at the very, very end, I would then plug numbers in. Okay. All right. So let's all right. So let's move on. Let's talk about equation of continuity. Okay. Whenever you have, okay, so suppose you have some pipe of some sort. This is some pipe. And suppose there is a fluid going, suppose there's a fluid that's moving in this pipe. So the fluid is moving to the right. And as you can see, this pipe changes its cross-section area. So the cross-section area here is A2, and the area here is A1. And obviously A2 is smaller than A1. And then the fluid, of course, is moving to the right. So the fluid's velocity at this area is V1. By the time it gets here, it is changed to V2. Okay, so now we want to find a relationship between the two velocities, knowing the two areas. Obviously, we know the areas because we built the pipe. We then need to know how are these two velocities related when the fluid is going in. And we're talking about, we are talking about incompressible fluids, which most liquids are. Okay, so most liquids are incompressible. Okay, so that's what we were talking about. All right. So, if you think about this, a little when this, let's say you're looking at this exact position here, and let's say that amount of fluid moves with that velocity a little bit, some delta x. Okay? In delta time. And then obviously the amount of volume in that. So the amount of volume in this little area of in this cylindrical area, that the amount of volume is equal to the cross-section area times delta x by very definition of volume. The thickness, which is delta x, times the cross-section area is the amount of volume. This is volume. Okay? So, because the amount of volume on the left-hand side of this pipe that goes through per unit time is the same amount of volume that goes through the right-hand side, the volumes do not change because this fluid is not compressible. So the same amount that goes in has to be the same amount that goes out to the other end. That means A1 delta x on the input on the left has to be equal to A2 delta x to the right. Okay? But delta x is V delta T. That means on the left-hand side, I have A1, V1 delta T, and on the right-hand side, I have A2, V2 delta T. Now, these are the same delta T's, so I can cancel them out from the two sides of the equation. And then I have the continuity equation, which says the cross-section area on the input times the velocity in input is equal to the same multiplication of two terms on the output. Okay, so this is the continuity equation. Okay, it means A cross-section area times the velocity at that point is not changing no matter what happens to the cross-section area. So therefore, A times V in general is a constant, okay, which is the continuity equation. It's another way of writing it instead of writing it specifically for this application. So A1 V1 is equal to A2 V2. That's always the case when you have an incompressible fluid. And that just says A times V is a constant. All right? Now, there's a name for this. This thing is called R sub V, which is called volume flow rate. Okay? This is called volume flow rate. It's the same number, volume flow rate, which is a constant throughout the moving incompressible fluid. And you can actually change this. There is another thing called R sub M, which is rho times R sub V, which is rho AV, and this is called mass flow rate. Okay, these are just definitions of different quantities. You know, A times V is called volume flow rate, and rho times that, which is rho AV, it's called mass flow rate. Okay, it's just, these are just two names for these two definitions. Volume flow rate is a constant. It, throughout every part of the fluid moving, no matter where it goes. And the only reason is it is a compressible fluid. So if it's a compressible fluid like a liquid, these are all valid constants. All right, so let's do an example so we know how to use a thing like this. All right. All right, so let's have a faucet. It's a faucet, and liquid water is coming through, and you all have seen it when the water is nicely coming down without any turbulence. It looks like this. So water comes down with this weird shape. It's larger on the top, and as it falls, it gets thinner and thinner. And so suppose we know the cross-section area at this point, and at this point the velocity, let's call that v1, of the water is v1. And let's say at some distance down, the velocity is v2, and we know it has a different cross-section A2. And let's say we have our x and y coordinates like that, and we know this distance in this x and y coordinate is just h. Okay, so now we want to find the relationship between the two velocities on the top and at the bottom of this flowing water, which is what we all see every day, probably quite a few times. But there is this interesting physics involved that we never think about, but this is where we learn all that. Okay, so first of all, A times V is a constant, okay, for an incompressible fluid like water. So that means A1 V1 has to be equal to A2 V2 in this situation. So this definitely has to be true, okay? But we also know something else. Obviously, right now, we have V1 and V2 are both unknowns, and we don't know how to solve them. There's two unknowns, V1 and V2, and we have only one equation so far. So we need another equation that relates V1 to V2. And what is that? How could V1 and V2 be related in any other way? Can anyone think of something? For example, if I knew V1, would I be able to find V2? Remember, water flows only because we have gravitational field. So if you have gravitational field that's pointing down, what would be the equation that relates V1 and V2?
Is it V2 squared is equal to V1 squared plus 2g change in t?
Thank you. That's exactly correct. After all, water is just like any other object that's accelerated downwards in a gravitational field. It's like dropping something from height h, then trying to calculate what the velocity would be when it finally reaches the ground. So this is obviously the equation that we all learned in 2A. And so there is another equation then that relates the velocities between the 2 points that are related by this. So V2 finally is related to V1. And H delta Y is y final minus y initial, which is 0 minus h. All right, so v2 squared is v1 squared plus 2gh. And so v2 is square root of v1 squared plus 2gh. All right, but then let me erase this because we can solve for v2 from the first equation. All right, so let me label these equations 2 and 1. So we can combine 1 and 2, and what we get is v1 squared is equal to 2gh a2 squared over a1 squared minus a2 squared. Okay? And then you can just take the square root of this thing and get rid of the square on the side. So that is your v1. And if you have those areas, you can see now you don't need anything else other than measuring the cross-section areas of the 2 points that are separated by height h. And all this is all geometric factors. The interesting thing is this is all geometric factors. So you can actually calculate the velocity of water as it comes out from the faucet by just making geometric measurements, which is pretty neat. Now, of course, we can have numbers. Suppose A1 is equal to 1.2 centimeter squared, A2 0.35 squared centimeters squared, and H 45 millimeters. And if you can then plug those numbers in, 2 times 9.8, H is 45, and then A2 0.35 centimeters squared. We have to do a factor here. 100 centimeters is 1 meter. And we square that, and we do the same thing at the bottom. Okay, and of course, you do all that, you get this number. Okay. So just by measuring geometric quantities like the areas of A1 and A2, now of course, if the cross-section of the outlet of the faucet is round, then by measuring that diameter, you can calculate the areas pretty easy. So all you have to measure is just those two diameters and the distance between them, which is h. Plug it into this equation, you know the velocity of the water coming out of the faucet, which is amazing to me. I mean, just measuring geometric objects gives you the velocity of water. It's just unbelievable. But that's the power of using a continuity equation. Any questions? All right. All right, so let's get to one more. And then we are actually done with this chapter. So Bernoulli's equation. All right. So at some point, Mr. Bernoulli did this derivation. So let's do the same thing he did, so we know exactly what we're looking at. We will come up with an equation that is yet another constant when it comes to incompressible fluids, just like continuity equation. So the continuity equation tells you in general that volume never changes. That's what that means. Now, Bernoulli's equation is going to relate all sorts of other things like pressures at the inlets and density of the liquid and all sorts of stuff. So let's hypothetically have some pipe that in this XY coordinate, now of course, Y is the height. So this is height. And there is also this gravitational field in this situation. So we're pretty much looking at a pipe that's carrying a fluid, which actually is going up in the gravitational field to a different height. All right, so let's find out what those heights are. So this height here is y1, and let's call it y initial. And then this height is y final. The fluid is moving like that in this direction. And the other parameters are, this has a cross-section area A1. The fluid has a velocity here, V initial. Let's call that A initial. And then on the outlet, it has a V final. The air cross-section area is A final. And going back to the inlet, there is also pressure at the inlet, P initial. And then pressure here is P final. So you can see this is a rather complicated, some fluid that goes from certain height Y initial to a final height of Y final, and pressure at the inlet is different, the area at the inlet is different, and then the outlet pressures and cross-section area, and even the velocities are all different. Okay, so now we want to find the relationship between all of these parameters, the inlet parameter and outlet parameter. Okay, so we all know that using work energy theorem, says that change in kinetic energy is equal to work done on the system. Okay. All right. Well, this is pretty easy. K final minus K initial is equal to W. Now, the question is, what is K final minus K initial? Now, if you think about a little portion of this, let me see if I have any other color that I can use. But, all right, so if there is any portion of this liquid, let's say there's this little portion of it, and that portion at the inlet becomes a little tinier portion because the area is larger at the outlet. Okay? Because their volumes are the same. So, but that little tiny portion at the inlet has some velocity that's moving to the right. So its kinetic energy obviously is 1/2. Well, this is the final, the output, 1/2. That little mass, which is that in that little sliver, times the velocity squared. That's just the very definition of kinetic energy. And that would be minus 1/2 the same amount of mass, because the mass, this is an incompressible fluid. It's the same amount of mass to the right, to the left in the initial inlet. Okay, so that's the left-hand side of this equation. Now, the right-hand side of this equation was a little bit involved, so you need to pay close attention. Okay? So, there are two contributions to the work done on the system, which is the term on the right. As this fluid moves up, as that little tiny sliver of mass of it, which I've drawn as on the left, and that little yellow portion, as that thing goes up from Y initial to Y final, gravity is working on it, and gravity is working on it. So, but the gravity is trying to pull it down, yet its displacement is positive. It goes up. So the amount of work done by gravity on that little portion is negative. Okay, so that would be minus mg, m is that little thing, mg, and the delta h, which is h final minus initial. I mean, I call it y, but so that's this is the amount of work done on that little sliver delta m. Maybe I should show that. That's delta m. So as that delta m moves up and ends up at the right hand side at the very top of the pipe, the amount of work done on it by gravity is minus mg h, and h is the difference between the heights. So that one's not that difficult to see. Okay, so but there's also another work done on this sliver of mass as it moves up. Okay, and that is the actual force that's pulling it up to that height. Okay, this amount of work that was done by the gravity is negative, and despite of this thing moving up, it's still it is doing work, but that's negative because it's trying to pull it down. But now the actual force that's pushing this thing up is going to do the work, and that work is equal to F delta X, right? So that one is, so I have to add to it an F delta X. This is the amount of work done by the external force pushing this thing up a little delta X. Okay? Now, this force, well, obviously is pressure at the input minus the pressure on the output times the cross-section area times delta X. And let me actually put this A on the other side so you can see. So you can see there. Now A delta X is delta V, which is volume. So now I'm going to rewrite everything on the left-hand side again. 1/2, and delta M is rho of the liquid times delta V minus 1/2. Let me actually do this. Let me get a rho of the liquid delta V times 1/2, and then I can just factor this out. And on the right-hand side, I get delta M again, which is rho of the liquid delta V, Y final minus Y initial. And of course, I have this term. And now delta V's cancel from both sides of the equation. And then I'm going to end up with this equation. Okay, so I just rewrote the equation with the things that I dropped out. So this is still the same equation at the bottom. I'm just cleaning it up. Okay, now I can gather up all the final initials on one side. So I can get P final plus rho of the liquid G Y final plus 1/2 rho V final squared is equal to P initial plus rho L G Y initial plus 1/2 rho of L V initial squared. So you can see this term, whatever this term is, at the final end of the pipe is exactly the same term at the initial end of the pipe. In other words, P plus rho G Y plus 1/2 rho V squared is a constant. This is another constant we just found. So this is called Bernoulli's equation. Okay, and then if you remember continuity equation is A times V equals a constant. All right, so now we have two equations that we know are constants when you're talking about incompressible fluids movement. All right, so let me get a screenshot. All right, any questions, guys? Only for incompressible fluids, like liquids. All right, so and I'm gonna use these equations tomorrow to do some examples. All right, guess we're out of time. I'll see you guys in the morning. Yeah, you have a question? Let me see. So no, we're not. Let me take a look. Chapter 14 is this one, and the next one would be 18. So next chapter would be 18, yes. All right, so I'll see you guys in the morning. Take care.